Judy Warner. Welcome back to this next edition of our DesignCon 2024 pregame podcast series. Today I'm really amped. Why? Well, because I have Steve Sandler on today, who's one of the world's leading authorities on power integrity. And he's been working on some amazing technology I think you're going to love geeking out on today. He's talking about how to measure 2000 amps, both at the chip level and the board level. And he's got products, he's got presentations coming up at DesignCon, and he will also have a booth there. I think you're going to love this conversation. Make sure if you are going to use our promo code is ECCO for 15% off. And make sure you come by and see us at booth 645. Now let's jump into our conversation with Steve Sandler of Picotest. Hi, Steve. So good to see you, my friend. It's been way too long, and I know we have so much to catch up on. It's good to see you.
Oh, it's great to see you, too. And yeah, it's been a while, and lots going on. You know, I see you online. I see all the things you're doing, and things move fast.
So fast. So we are here because DesignCon's coming up, and that's a huge show for you and for Picotest. So I wanted to get you on and share with our audience what they can expect out of you this year. And I know it's been a busy year for you as well, just judging by LinkedIn. So I'm excited to talk about it. So why don't we start off by talking, Steve, about the sessions, the presentations you're giving. And then let's talk about your products, because I know you have a bunch of new toys out.
Oh, yeah, new toys. Yeah, so, you know, DesignCon is like home for me. So I'm very involved, and I usually do a lot there. So this year's not any different. I have 3 sessions. I have great participants. So, you know, mostly Heidi and Ben. We brought in some new people this year. We brought in Eden Ben Israel from Broadcom Israel. We brought in Uni from Monolithic Power Systems. We brought in Jason Sekanina from Analog Devices. So, you know, tried to round up a really good group of people to put our finger on the pulse of what's going on. And so these 3 sessions, one of the sessions is about what does it actually take to design a 2000 amp core power rail. And it seems like so out of scale, right? You know, CPUs 300, 400, 500 amps. You know, how do we get to 2000? When did that happen? But what does it mean? And how do you design that? You know, so the first paper is a paper on exactly that. How do you design, simulate, and validate a 2000 amp core power rail? And it gets into everything from electrothermal simulation to package simulation to VRM design and all of that. So we have a great paper on that. We have a panel discussion. The panel discussion is going to be really interesting too, but it's also about this crazy 2000 amp data center AI world, but from the perspective of what does this mean for engineers? How is this changing their lives? How is it impacting them? You know, they're already super busy doing the things that they do, and now they got to do even more things. And one of the bigger challenges is that we all have to do things that we don't know how to do. You know, a lot of this is new and at levels that nobody's ever measured before. And then we have a calibration session because our customers that are, you know, building these boards, they're having trouble making these measurements. How do you measure 30 microns? It's a really small number. And so it takes a lot. It takes calibration, it takes isolation. And so we worked out the mathematics of that. We validated the measurement, and so we're going to present that in a Chip Ed Theater presentation. And you're right. I mean, we've been really busy, you know, building these new products for this space. And partly, you know, the way Picotest works, it's really simple. Customers come and say, I'm going to do this. We don't know how to do this. You got something for that? And if, you know, if the answer is no, I usually follow up with, but I can make that. And so there's been a whole lot of, but I can make that this year. And so we want to show that off. And so for that same reason, we have a booth at DesignCon. And this is the first year that Picotest has had a booth at DesignCon. So in fact, we just had our very first booth at the Supercomputer Conference, and that was our first booth anywhere since 2014.
Wow. So it looked really good. It looked really good, by the way. I was cyber stalking you guys on LinkedIn, and it looked wonderful.
Yeah, you can thank Emma for that.
She did a great job.
between Emma and Charles, they really did make it look good. And the thing about these conferences, and most of these are new conferences for us because it's a new product world. We haven't really been involved that much in AI and data center, but there's a lot of need there, so we got involved. And being in a conference like the Supercomputer Conference and DesignCon lets us hear from engineers about what kind of problems they're having. And it ranges all the way from really simple problems to really tough ones. And our job is to stay out front and try to help people navigate these issues and figure out how you measure it. So
I want to ask you about that because we touched on it before we started this recording. So let's go back to your point about 2,000 amps and data centers and AI. Can you tell us the backstory about how that's emerging and why we're even talking about 2,000 amps?
Yeah, so I mean, it really does seem like out of place. It's like, how'd that happen? When did that happen? And so, we've seen AI coming for a while, and, we see everybody building bigger data centers. And so it's not that we didn't know this was coming. It's that it's growing faster than anybody expected it would grow, and the demand is growing faster than anybody expected. At the root of all this, I think that NVIDIA probably started a lot of this escalation by themselves. NVIDIA made great GPUs, graphics processors for mostly for gaming, right? They made the fastest GPUs in the world, and it's a relatively newish company, but that's how they started building GPUs. But they got this idea that if graphics processors are fast, maybe we shouldn't use CPUs in these data centers and AI. Maybe we should be using graphics processors. So NVIDIA started selling these GPU boards for computing, and they have one called H100 that is about 1,000 amps, just under 1,000 amps. And it became crazy popular. Almost everybody is using that board now.
Wow.
And that forced AMD and Intel to try to play catch up and, build bigger processors. Well, the H100 was already at about 1,000 amps. And so how do you kick that up? Well, you go to 2,000 amps, right? That's only doubling it. And at the Supercomputer Conference, we saw a lot of people that are doing 2,000 amps. We even heard from one customer that's doing 6,000. So, yeah, talk about reaching for the moon. We do know, or at least we hear rumors, that NVIDIA's next board is at about 1,500 amps average and a little over 2,000 amps peak. So these power levels are getting really crazy. And that's done a lot of things to the industry. One is that, these processors are really fast. That means we've got to spew data even faster. So all of a sudden, we're putting a lot of pressure on faster transceivers. And I think NVIDIA played a big role there, too. I think they're the very first 3.2 terabit transceiver. And that's causing its own measurement problems, in the optical transceiver world. And how do you measure these things and power immunity and all of that? But it really comes down to, all right, so we got to do 2,000 amps, but how? We don't really have VRMs that you go to DigiKey and say, I'll take a 2,000 amp one.
Right.
Then you have the semiconductor industry that's being pressured just like everybody else. Customers knocking on the door saying, hey, we need more power. Infineon, I think it was a year ago, announced that they had the very first 1,000 amp controller. And I don't know why they claim that, because people have been doing 1,000 amps, for a while. But Infineon jumped on the bandwagon and said, wow, we can do this. 32 phases of VRMs. I think that Microchip is working on 64-phase VRMs and digital controllers. I don't know if they have that yet or not. And every company is trying to figure out how do they fit in the mix. And so we're going to be showing that. In fact, I got some props here. So here's one 2,000 amp puppies. And you can see all of the MPS modules. And what they did is they put all of this into computer-controlled modules that are sort of plug and play. And then we can connect the computer to them to tell them how we want them to operate, what voltages we want, what kind of monitoring we want, what kind of whatevers. And then Well, these power levels, you can't really run at 12 volts like most computers do. So they run at 48. So we need these 48 volt, converters that you see smattered around. That's all, high-speed gallium nitride. But then how do you test this? These are really fast boards. So they came to us and said, how do we do high-speed transient testing at 2,000 amps? And that's what Picotest made. Picotest made this gallium nitride ultra-high-speed controller. And inside these modules that Monolithic Power made very easy for us to use, there's 55 phases of power supplies. They just did all of the management for us.
Wow.
And, well, other companies like Analog Devices, they weren't going to get lost either. So they came up with their own module and said, we can do better. What if we don't have to have those 48 volt things, but what if we just went directly from 48 to 0.7? Then we could make it even more efficient. We could make it a little less expensive. And so we built that one also, and you can see our 512 load cell array. But this is where it led to. And so, I think at DesignCon, everybody knows about target impedance. We talk about target impedance all the time. I've given a bunch of papers, on target impedance and road waves myself. But now you start looking at this in 2,000 amps, it's 30 microhms, 30 microhm target impedance. How do you measure 30 microhms? And so it turns out that's not so simple. But, that's what Picotest does. And we figured out the mathematics of how you measure 30 microhms. In fact, we even figured out how you measure 30 microhms with our probe. And so we'll be showing that at DesignCon also. But it's all of these things that are, interplaying and interacting, making this really challenging. At the same time, the bar is moving as fast as we're catching it. It's kind of like a hamster on a wheel. That's how I feel right now, like a hamster on a wheel.
Well, it looks like FOMO is working out pretty well for you this year. Everybody wants in, right? And you're the people to get it done.
It's been a really busy year, I'll say that. And we are kind of the measurement experts, and we are the power integrity experts. And so a lot of people come to us, trying to figure out how do you do this, but it's new for all of us. So it's like,
right.
Hang on, wait here. I'll go figure it out, and then they'll let you know. And, it flows all the way down to how do you measure the 48 volts? Because our probes aren't really made to do that, at least not for high speed. And when people try to do that with RFDC blocks, they're breaking your oscilloscopes. And so they came, can you fix that? And so we did. We made the first port saver for oscilloscopes that allows you to measure 48 volts without breaking the oscilloscope. It comes down to how do you build these load cells. So, we finally mastered how you build load cells, and almost everything that we introduced this year is water cooled or refrigerator cooled. It's
Did you ever imagine even 5-10 years ago that you'd be here, Steve?
No, not at all. In fact, when I finally realized that I had to make the first water-cooled probe, I questioned myself for months. It's like, does this actually make sense? But it's not like you have a choice. You just keep running forward, right? And our goal at Picotest is always, how do we get the customer where they want to go? And that usually means, what's in the way? How do we move it? And, what that really entailed is to get to the frequencies they want, we can't have long interconnects. They got to be really short. We need our devices to be very close to their dot. That's how it became a probe. If we can make it into a probe, then we can get really close to their board and we can get them the bandwidth they want. But there's a lot of power in there. So how do we get the power back out? And the only way we could do it without physically impacting the size of our products, we could stay close to the board, was to water cool them. And so everything, even our PSR modulators now, you can see the water cooling lines, and everything has, modulation water channels in them, and you can see the bolt holes are getting bigger and a lot more challenge for our mechanical engineers who design all of these water manifolds that create these crazy thermal densities. So, you don't really think about it, but we need these high-powered things to make this measurement, and we need it to be high speed. So thank you, Alex Lido, for making gallium nitride. It gives us really high speed, high power devices. But the device in there is only about 12 square millimeters. It's tiny. It's the size of a 1206 chip or something, right? And we just spent more than 100 watts in that. So the power density,
Unbelievable.
the amount of heat that we have to remove is crazy, absolutely crazy. So we're working with all kinds of engineers and physicists to figure out how we can best manage the air gaps between the devices and the manifolds. How do we get the right amount of water? How do we make a cooling system that's reliable? And so I'm not showing it here, but hopefully at DesignCon we'll show our first water cooling system that's Picotest branded. And we designed that from the ground up too, to support our probes. So it's just the way we work. Tell us what you need to do. We'll figure out how to get you there.
I always think of you like a crazy scientist, Steve, but making the coolest stuff ever. What do you think's missing? Like, as we move towards this crazy 2000 amp, and how's the rest of the ecosystem coming up around that? Like, where's the other pitfalls?
Yeah, so it's really interesting. And I think actually it's been really helpful in a lot of ways. So, the semiconductor industry, for the most part, really wanted to avoid all of this power integrity nonsense. It's just a power supply. But they're getting sucked into it, right? These 2000 amp boards, the semiconductor guys got sucked into it really bigly.
Yeah.
Because we need to come up with 2000 amps and quick. So that kind of brought in the semiconductor guys, and that'll carry an awful lot of weight, and it'll help the industry a lot. Printed circuit board design for this stuff is very different than, traditional kinds of things. And most of our simulation now involves electrothermal simulation, which we didn't have before. And so Heidi's going to talk about that at DesignCon, electrothermal and also EMI. You start switching 2000 amps and that radiates pretty good. So there's a lot of that missing. And there's also a lot of knowledge gaps. I don't want blaming engineers for that. Even us, when people say, how do you measure 30 microns? I don't know. I really don't know. But it's all math, and I actually did publish that math, and I think it was 2017. I did a university course at DesignCon on measuring below 100 microns. I had developed the math, so all I really needed to do was run my equation and see what it took. And what it took is ridiculous amounts of common mode isolation. So we're showing a new common mode isolator that you need to measure below 100 microns. But we're all learning, and I think we need to resolve these knowledge gaps in order to get from here to there. And we need to better define the problem. What is the problem we need to solve, and how do we get there? So, we talk about ultra-high-speed excitation. So, there were load slammers like Load Slammer. In fact, we're a distributor of Load Slammer. And I was pretty good at testing voltage regulators, but this isn't about voltage regulators anymore. This is about testing power distribution networks. I need the whole network
Right.
to go to 2000 amps. I need to be able to test it thermally at 2000 amps. So, this is something we need to do 2000 amps steady state. We need to be able to do it high speed. And so we're doing 50 megasamples per second at 100 megahertz bandwidth, package speed. So is package speed fast enough? What is package speed? It depends on the device. Different devices will have different speeds. But it seems like no matter what we do, there's somebody that says, can you do more? We showed our 2000 amp high-speed step load at Supercomputer Conference. We had a customer asking if we can get to 5,000 amps. We said we're 100 megahertz. They said, can you get to 300? It's just the way engineers are, right? You give them an inch and they want a foot. You give them a foot, they want a yard. You give them a yard, they want a swimming pool. It's just the way it goes, right? So we're just going for the ride.
Amazing. Well, good for you for getting out on the bleeding edge ahead of all of this. And it looks as the last time we talked, it's gone wild.
Yeah, it's growing.
You really start developing this quite early before this whole story you just unpacked about NVIDIA. So you're going to be showing all those products at DesignCon, I assume.
Oh, yeah.
Oh, yeah. So for our listeners, if you're attending, make sure you go see the Picotest booth and go see all these products, especially for those of you that may be listening on audio, because he just showed the coolest stuff. And if you're just listening, go look at YouTube or make sure you go see Steve at the Picotest booth or his presentations. Steve, before I let you go, I'll definitely send people to all the DesignCon stuff and your website. What else do you think engineers should be paying attention to, and where would you like me to link to so people can keep up with you and all the stuff that you're doing at Picotest?
For all of the conferences and recent presentations, we've actually been making little key fobs with QR codes, and the QR code will take you to a page that has everything we showed. So I don't have that link handy, but I'm sure Emma can get you a link that would get you to a page that'll show everything that we have going on at DesignCon and everything that we showed. So if you want to find information about something you saw at DesignCon, you can go there. Have some really great panelists this year. We've got a lot of really good discussions. We're going to talk about how all this is impacting engineers today, and it's not going to slow down anytime soon. It's just going faster and faster, and our job is to keep up and not be in the way, right? So, it's like keep up or move over.
Yep, it's true, and I never cease to be amazed. And it's always a delight to talk to you because you're always out there way ahead of the pack, I guess, because people are coming to you like, I know, Steve could do it.
We do get a lot of that. And I do lose a lot of sleep over some of this stuff. And, the actual load cell, I've been working on that for 3 years. We knew this was coming. It just took us 3 years to figure out how to cool it and how to get to the speeds that we needed to get to and whatever. And we actually sent Alex Lido one of these gallium nitride loads so he could see a board with 512 of his devices on it. And he's like, that's absolutely amazing. And I said, it's your device. I just put them on a board, right?
Yeah. So, well, thank God for people like you and Alex Lido. By the way, for our audience, if you haven't heard of Alex Lido, he invented both the MOSFETs but also power gallium nitride. And so I did a podcast with him before, but we're going to do another one. And I'll have him unpack what that looks like from his end to see your thing show up on his doorstep. And
and he's one of my favorite human beings because he's so down to earth and so approachable. I don't know how many people could say, oh, yeah, I invented gallium nitride and the MOSFET, but yet he's still approachable.
Yes.
He's older than me, and I think he still has more energy than I do. So he's just always so much fun, but he's one of my favorite people.
He is lovely, and thank you so much for introducing me to him. He really is, yeah. He does take it all in stride, and I appreciate that about him, and also you, by the way, because the things you say that you do in passing crack me up. I'm always trying to keep my mouth closed so my chin doesn't drop open. I don't know if I succeed very much. Well, Steve, congratulations to you and your small and mighty team at Picotest. You guys do phenomenal work. We're also grateful that you're here to do these amazing things. And thanks so much for coming on the podcast. And I look forward to seeing you at DesignCon in just a few weeks.
Yeah, just a few weeks away. And it's always a pleasure to see you. It's always a pleasure to be on your podcast. You're just such a great interviewer and you make it so easy. So anyway, I enjoyed the time we had together, and I hope to see a lot of folks at DesignCon this year. And pay attention. If you pay attention to what people are showing, you can see where the world is going.
It's pretty amazing. I'm really looking forward to the show for that reason. So thanks again, Steve. For our audience, as I said, I'll make sure and put all the links for you below in the show notes. Thanks for joining us again today. I hope you enjoyed this conversation with Steve Sandler, and we both hope we'll see you at DesignCon. Until next week, remember to always stay connected to the ecosystem.